Okay, very good. So we can see your slide. I think we can also hear you. And same thing, I will check both in the room and online if there are any questions or comments and may interrupt you. And I will give you a timer 10 minutes before. Does that sound good?
Yep, sounds perfect.
Fantastic. So then we have our next speaker, Jay Kalinani, who will tell us about AsterX, a new open source GPU-accelerated GRMHD code for dynamical spacetimes. So please take it away, Jay.
Oh, thank you, Helby, and thanks, Levi, for a great talk. So hello, everyone. My name is Jay Kalinani. I'm a postdoc at Rochester Institute of Technology, working in the group of Professor Manuela Campanelli. And firstly, I would like to thank the organizers for giving me this opportunity to connect with you all online and talk about our code called AsterX. This is definitely a collaborative work involving many people that I list here. And we also have a paper on AsterX on CQG as well as on archive in case you would like to check it out. And also feel free to interrupt me at any point during the talk. And also you can reach out to me in the future also through my email if you have any questions or curiosity about AsterX or otherwise. So just to give you a brief overview about this talk, I decided to include some background information about GRMHD for people, catering to people who are new to this concept. And GRMHD essentially stands for General Relativistic Magnetohydrodynamics. And then give an idea of how a very rough structure or workflow of how a code like GRMHD works. And then I will jump to our code called AsterX and show you some test results as well as performance benchmarks and a very, very quick introduction to our new code called NewX. So just to have some suggestions for resources for books related to numerical methods, we have the standard LEVEC, and then there are books on numerical relativity, as well as there's a book on relativistic hydrodynamics, but by Rezzo Lanzanotti, in case people would like to check that out. There are also articles available online on archive and otherwise from different authors that talk about GRMHD as well as numerical hydrodynamics. So just to leave it here in case people would like to have a more complete introduction on the topic. Now, just to motivate, why do we care about GRMHD simulations? So GRMHD allows us to model different astrophysical systems involving crucial magnetohydrodynamic effects. For instance, if you would like to model protoneutron stars or bioneutron star mergers, at RIT, our group also focuses on one of the projects based on modeling gas accretion around supermassive binary black holes mergers. And there's also a recent paper out by Lorenzo and Oggi, if you'd like to check that out. And then next, if you also want to model any magnetohydrodynamical magnetic instabilities like MRI or Kelvin-Helmholtz instability or magnetorotational instabilities, you can do that through GRMHD. And my favorite topic is also to model jets. So either from a remnant neutron star, post-merger remnant neutron star, or even from a black hole around an accretion disk. So that's the main motivation to do GRMHD. And now the next question is why GPUs? So until about 10 to 15 years ago, most of the supercomputer architectures which is the fastest ones, were based on CPUs. But there has been a major shift to GPU architectures, and now if you go online and check, at least about 9 out of 10 fastest supercomputers are based on GPUs. And of course, there is advantage in terms of AI, but also for HPC and for academia. And one of the reasons that Dr. Lee pointed out that our simulations now can be at least 10 to 15 times faster. So imagine if you're doing a simulation that lasts for a year, can now be finished within a month. So that is definitely an advantage to jump to GPUs. Now, let me touch base on a bit on the numerical background. So here we care about solving Einstein field equations along with Maxwell equations for electromagnetic fields. And for the hydro, you have also the energy conservation as mass conservation equations. And the typical approach, as you may already know, is this 3+1 foliation technique, and treating our problem as an initial value problem, where we provide some kind of an initial data, and then that's kind of evolved in time. And to do that, you have many space-time evolution codes in the market based on BSSN Z4C formulation, like Baikal, Canuda-X, McLaughlin Z4C. Now, Leeway also talked about a couple of them, and also we have Lucas's code as well. And for GRMHD evolution, typically they are based on what is called as a Valencia formulation. And you have other codes, some codes in market, such as Whiskey MHD, Illinois GRMHD, GRHydro, Spritz, and Greyhole that Leo will talk about, I think, later today or tomorrow. Now, one of the first steps that you do is, once you provide the initial data for your problem, you typically provide it in terms of rest mass density, fluid velocity, specific internal energy, and if you care also about electron fraction, which is essentially a ratio of the number of electrons to number of baryons, then you can compute what we call as the conserved quantities. These are the quantities we are interested to evolve in time. And for instance, what here is what's a conserved density. You have conserved momenta Sj and internal energy, as well as magnetic field and electron fraction. So these are essentially the analytical prescriptions to compute the conservators from a primitive. And this is one of the first steps you do once you start your evolution using a GRMHD. Of course, I'm not talking about space-time here. These are only related to the hydro quantities. Now, most typically, most of the GRMHD codes are based on this first-order flux-conservative hyperbolic Valencia formulation, where you have here U as the state vector. And these are essentially the ones I talked about before, the conserved density, conserved momenta, conserved energy, etc. And then F here stand for FIs are essentially the fluxes for each of these state vector. And these are the expressions for the different fluxes. And then S stand for the source terms. And when you see that there is a non-zero source term, that means essentially a fluid can have a feedback on the space-time. So essentially fluid can interchange energy and momenta with the space-time itself, where T mu nu is just a expression is given in such a form. And here alpha is the lapse, and gamma is, I think, the determinant of the 3 metric. Now, to talk about the evolutions equation for the magnetic field. So typically, GRMHD codes are based on the work under the assumption of ideal MHD, considering that your electric conductivity goes to infinity. And in that case, the co-moving observer that is moving along the fluid measures no electric field. And in that case, you can rewrite your Maxwell equation solely in terms of the magnetic field, B itself, in this form. And then you can also break these equations into a divergence-free conditions. Essentially, you don't want to have any magnetic monopoles in your system, excuse me, as well as the induction equations of B, how B is evolved in time. And here on the right, I just show these co-moving magnetic field components, small b, written in terms of the Eulerian B, which is the big one. Now, some codes might choose to evolve what we call as A, or vector potential, instead of the magnetic field. And in that case, you have your 4 vector potential written in this form, where you have phi as your scalar potential, and then A nu as your 3 vector potential. And then you have induction equations for the vector potential itself. And that's what's been evolved. And once you have your vector potential, you can compute B from the curl of A. Now, the advantage of doing this is, by construction, if you take the divergence of this equation, then by divergence of curl of a vector is essentially always 0. So by construction, you would not allow magnetic monopoles in your evolution. Now, to evolve the induction equations of A, you also need to provide some kind of a gauge. There are different gauges in market. For example, the algebraic gauge, where you set this phi equal to this. And then there is also a more robust gauge, which is called the generalized Lorentz gauge, where you have this equation for the covariant divergence of the vector potential, like written like this. And in this case, you also need to evolve an extra evolution equation for the scalar potential like this. Now, to close the system of equations for the GRMHD system equations, you also need to provide the pressure for in the system. So the most common are the analytical expressions for pressure, for example, the ideal gas or even polytrope. And then there are also hybrid equations of state in market where you have P as a function of rho, which provides the cold part, and then a thermal component. And for example, if you want to model neutron stars, as you see, so on the right, you see the P as a function of rho for different kinds of equation state, some of them only that exist in the market. And this is essentially what we call as a piecewise polytropic approximation. A more sophisticated equations of state come in the form of tables, like essentially the three-parameter equation of state, where you have the pressure dependence on density, temperature, as well as electron fraction. Now, all of this was just to show you what kind of equation was evolved. Now we want to evolve these equations on a grid, so you want to discretize. So imagine you have a numerical grid as on the left. On the x, you have essentially the spatial coordinates, and on the y-axis is the evolution or a time update. And you typically store your state vector at the cell center, and then you try to evolve that in time, and you compute your numerical fluxes on the cell interface. Now, as Lieve also mentioned, for example, when you go to a 3D grid, you have the possibility, especially in CarpetX, to store your variables at different positions, not only at cell center, but you can have your variables at vertices or on edges or faces. So this is what I show here. For instance, here in the cell centers, you have UIJK, which essentially takes care of storing most of the hydro variables like density, velocities, etc. Here on the vertices, we typically store the spacetime variables, and also the staggering allows us to store the vector potential on the edges of a face. And then when you take a curl, for example, on this face, you immediately get the B computed on the cell face itself. And this staggering allows us to be consistent with when we want the B to be computed at the cell face. Now, since this was the previously when I showed a differential form of the equations, one can write instead an integral form of these conservation equations, neglecting the source term, and then you discretize your state vector u and j in this form, as well as you can compute your numerical fluxes in this way, and essentially you end up with a discretized conservation equation that you can evolve on the grid in this form, where you have un+1 is your state vector at the next time step, using what you have for your un at the current time step, as well as the fluxes computed at the cell interfaces. Now, most state-of-the-art GRMHD codes implement something called as high-resolution sub-capturing techniques. So imagine you start with a very smooth initial data, but then once you, depending on the system in hand, it can happen that you develop shocks and discontinuities that develop. And to capture this, any numerical scheme that you implement in your code that converges should obey what is called as the Rankine-Hungarian jump conditions across these discontinuities. And this is what we typically call as a shock capturing property. So I don't want to go in detail of what these conditions are, but essentially what you want to guarantee is that for your numerical scheme, it should provide the correct propagation speed for these discontinuities. And essentially the Rankine-Hungarian conditions, jump conditions are given in this form, where you have the differences of your fluxes from left and the right side of the discontinuity is given as the speed of the discontinuity times the differences in your state vector. Now, once you have, so based on this, if you want to compute your fluxes at the cell interface, typically codes follow these two-step methods. What they do is something called as a reconstruction method, where you have your grid variable, suppose like density, you interpolate it to the left and right from the cell centers to cell interfaces. And typically, the methods in the market are such as the min-mod one, or more accurate piecewise polytropic method, we call as PPM. And then once you have your constructed variables at a common cell interface, you apply what we call as Riemann solvers, approximate Riemann solvers, to compute the fluxes at that common interface. And there are different, again, approximate Riemann solvers like Lax-Federiks as well as HLLE. So give you a quick example with the very simple reconstruction method. For example, you have for a given solution un, you can compute what is called as a total variation, and then like this, and then as you continue to evolve the system, your total variation of the state vector should not develop any spurious oscillations. So essentially, your total variations should be always not increase in time. And there are methods that obey such a property, and which are called slope limiter methods, and one of them is called min-mod, and that's what I show here. Essentially, what you're doing in min-mod is, for example, on the plot on the right, imagine you have a cell at J and you have this grid point. You want to reconstruct the values of this at the left interface and on the right interface. And you do the same game for the adjacent cell, which is at J plus 1, and you do reconstruct it at left and then at the right. And then at their common interface, you have the two values, and this is what we call as a Riemann problem. And discontinuity is developed. And similarly, the PPM method, instead of having a linear function, you can use parabolas to reconstruct your grid variables, as shown in this diagram. And next, once you have your Riemann problem set up, there are different ways of computing how to then compute the flux. For example, one of the standard solvers, what is called this HLLE solver, which assumes what is called a two-way approximation. So imagine on the right, as you have the diagram, you have a discontinuity at t equals to 0. And once discontinuity starts to evolve in time, you imagine that there are two waves that are evolving with the different speeds, called lambda L and lambda R. And this develops a constant third state in the middle, which we call as the HLLE state. And there are some expressions on how you can compute lambda L and lambda R. I don't go in detail. You can ask me later too. But then once you have these three states that are developed, when you can compute your UHLLE, this is your state vector, and for the third state. And there are some conditions based on which you decide which kind of state vector value to use. And then you can also compute your FHLLE using this condition. And then at the end, you have your fluxes either from the left or the right, or the FHLLE F star in this case, based on these conditions, if they are satisfied or not. And the simplest Lax-Federiks solver is essentially HLLE, but assumes that the left-going wave and the right-going wave have more or less the same velocities. The last part and one of the core elements of any GRMHD code is something called as a con-to-prim, conservative to primitive variable recovery. And at every time step, we want to understand what are our primitives. So we are evolving conservative variables. So we need to recover these primitive variables. And in GRMHD, there are no analytical solutions that we could find, at least up to now. So one needs to resolve to numerical approaches such as root finding algorithms. And many of these C2B schemes could fail at some point, like at the very high magnetization or Lorentz factors. But so here, Siegel et al. Has a good review on different C2P schemes, in case you'd like to check it out. But typically, they follow these two methods. Either they're based on Newton-Raphson methods, where you start with an unbounded root, and then you provide an initial guess, and then it might computing the root can also depend on these equation of state derivatives. And you have a more different method, which is called the root bracketing method, which are a bit more stable but slower. And you start with the bound and root. You know the bounds already where the root will be. And but these root solvers are not typically not based on initial guesses and on US derivatives. So just to give you an idea of what a quantuprim looks like, for example, this is the one from Noble et al. 2006. As I mentioned earlier, we want to recover some of the hydro variables. Essentially, the 5 hydro variables here are density, the 3 velocities, as well as, for example, specific internal energy. And Noble et al. Reduces this problem to 2 dimensions. So they introduce these 2 quantities, which are called Z, which is excuse me, a rho h times Lorentz factor square, as well as v square. And they have 2 equations based on these 2 unknowns, and they try to solve it by these Newton-Raphson method scheme. And once you find the roots for these for the 2 quantities within the specified accuracy that you can provide by a par file, you can compute your densities as well as velocities as well as epsilon using expressions like these. Now, to summarize and give you a very brief idea of a very rough schematic of how a GRMHD code runs. So this is the kind of equation we are trying to solve. This is a reminder. Now you provide your initial data, defining primitive variables at each grid point. You then do a prim to con to compute your conservative variables from the primitive. Now you can compute your source sums that I had mentioned earlier based on the expressions, which also involve derivatives of the space-time variable. So you use finite difference schemes for that. And then you want to compute your fluxes at the cell interfaces. So you use these high resolution shock capturing methods. Now then flux minus source essentially gives you an ODE in time that you can evolve using a time integrator such as RK4, for example. And then the last step is to do the con to prim to compute the primitives for the next time step. And then you keep doing the same game, you keep evolving your code. Once you have your primitives, then this is essentially a loop until you end up until you want to see the solution that you require. Now, before jumping to AsterX, just wanted to engage if there are any questions or comments.
Okay, let me check. Are there any questions in the room? No? Anyone online? No, I don't see any questions. So I think you can continue. Thank you, Jay.
Great. Okay. So GRMHD part is clear. All right. Great. So now we jump to AsterX. So as Lieve already talked about, and also previous talks, the basic infrastructure that is provided is by this code called AMReX, which is essentially a software framework that is developed by this massively parallel block structured adaptive mesh refinement applications as a part of DOE's exascale computing project. And it has different features that AMReX provides. I think Lieve gave a good talk on this, so probably don't cover that. And then on top of AMReX, you have this new driver for the Einstein Toolkit, which is called CarpetX. Provides, again, through AMReX, it provides support for GPUs. There's a local AMR criteria that you can define, the user can define, as well as it is aimed for exascale computing. And there is the option for hydro refluxing as well, as well as usage of elliptic solvers. And again, this code is publicly available that one can check out here. And it has already seen many applications already from multi-patch to WaveToy-X, and even they have many different space-time solvers. There is another GRMHD code called GRMHD by Swapnil Shankar et al. That, in case you'd like to check that out. And here also on the right, I show like a sample, an example of a simulation that one of the graduate students at RIT performed for a BBH simulation using Z4C. And his name is Alan Wen. So it has indeed promising applications, as well as CanudaX. I'm sorry if I forgot to mention your code, but yeah, there's been a lot of great developments based on CarpetX. And one of the developments, again, on CarpetX is this new GRMHD code called AsterX. Now, AsterX is Aster essentially is one of the flowers, which means star in Greek, and And also, so this is why one of the reasons why when we do, so for example, neutron star mergers and things like that, that's one of the reasons why we chose this name. And this is heavily adapted from another CPU, carpet-based code called Spritz from Cipolletta, Bruno Giacomatto et al. And we've tried to keep the structure of AsterX as modular as possible. So we have different modules or thorns for example, for reconstruction schemes. So we have a thorn called ReconX, which provides these different reconstruction schemes like MinMod, PPM. There is also VNOZ and MP5. Next, we have the flux solvers that I also talked about for solving the Riemann problem. Then we have a separate module called Contoprim Factory, which provides these different contoprims that we, for example, from Noble et al. Or Palenzuela et al. And we have also integrated, there is one from, which is there's a backup intro contoprim based on entropy evolution. And we also have support right now for reprimand, but only it's CPU compatible. Then we have modules for the equation of states, which is called as EOSX, which provides support for us. The simple analytical equation of state, the hybrid one, as well as now the finite temperature tabulated one as well. And we are currently testing these implementations as we speak. Then for vector potential, we have an option, evolution. We have the option of computing the electric field through the standard flux CT approach, but then this can be a bit say error prone. So then there is the more robust upwind CD approach as well that has been implemented. Next, we have what we call as an atmosphere, a graded atmosphere. So typically, GRMHD codes provide a prescription for an atmosphere that is typical constant in rho, but this can be a problem when you are actually evolving, for example, jets or matter that is very low density, which has very low density, as this can act as a hindrance. So we have instead now a graded or a radially dependent prescription for density, pressure, as well as temperature. And again, the AsterX development is all publicly done as well, and it is available through here. And unfortunately, I don't have any tutorials for this talk, but there have been notebooks that have been developed in the past for the previous schools that one can check out, and I'll paste the link here. So we tested AsterX through a series of one-dimensional, two-dimensional, even three-dimensional problems in a flat spacetime as well as in curved spacetime. So these are the standard tests that I show, which are called as the shock tube test, the Baltzara shock tube test. And these are the test suite. And we see that the profiles, for example, here match quite well compared to the exact solution what we expect for example, for density on the left and for the y component of the magnetic field on the right. Next, we did some convergence study as well when we evolved an alpha wave without shocks. And as you increase the resolution, we see at least AsterX converges to at least second order using, for example, MinMod scheme. So then for 2D tests, we considered a cylindrical explosion test as well as magnetic rotor, and we find that these profiles do match well with what we find in literature. We repeated the magnetic rotor test also with refinement, adding AMR, so box in box. And we see that we don't see any problems around the refinement level boundaries in this case. And this is a very stringent set because you have your matter moving with velocities of like 0.9, 0.99 c. So we still don't see any AMR issues, at least for this test. Next set of tests we did was like a loop advection, magnetic loop advection test. We evolved this loop through the domain with periodic boundary conditions, and it comes back to the same position after, say, 24M of evolution. And we see that, of course, there is some dissipation because I think we use MinMod for this. But this is kind of expected results that what we see also in literature. And as Lucas also showed in his slides, we are able to do something called as a Kelvin-Helmholtz instability test with dynamical AMR. So this was just to see if AsterX works well with dynamically evolving your mesh refinement or not. And here you might see that it is able to capture these curls that are developed in time, where you have these shocks produced, and you are refining in that region. A next set of tests was like a 3D TOV, magnetized TOV test that we evolved. For example, left is the rest mass density, and on the right is the X component of the magnetic field. And they seem to evolve fine. So here, for example, for the same tests, we repeated this test for different resolution for a convergence study as well, and see that on the top left, I show the evolution of the maximum of the rest mass density. And as you increase the resolution from blue to red, we see lesser dissipation, as well as the oscillations are maintained within within 1%, as compared to the low resolution case, which is really bad. And once you do the Fourier transform of this maximum rest mass density, you get this PSD that I show on the right for these different cases and for different resolutions. So as you move to high resolution, you're able to capture what these the oscillations of a TOV well and this vertical line show the values what you get from like a perturbative code, which is and they match well with what we get from a simulation with increased resolution. Recently, there has been development of a leakage scheme for photons, spearheaded by Mikhail Shabanov, and he's ported the code of Luciano Combi to AsterX. And here, just to give you a brief introduction, here we compute this leakage scheme affects only the T mu nu on the RHS, and where Q stands for this photon energy rate per volume. And for that, we use a transition functions to jump between the diffusion regime, which is called QDiff, and a free streaming regime where you have photons just free streaming. And when you have your optical depth, essentially what is given by tau, which is much greater than 1, that means you're in the diffusion regime. And once this optical depth is less than 1, you're essentially in your free streaming regime. Now, for simplicity, in the beginning, we consider only the diffusive regime and consider Q free to be 0. And we take only the Thomson scattering, essentially the scattering, elastic scattering of the electron from, for example, the nucleus or an atom. So you consider only the opacities, the optical depth and opacity only for this Thomson scattering in this case. So I think Mishi is still continuing to test this implementation, and he's also implemented code for a Fishbone-Moncrief accretion disk. And this is, for example, snapshots about 3000 m of evolution. On the left is the density, in the middle is the absolute value of the radial velocity, the z component of the velocity, and on the right is the z component of the magnetic field. So as you see that as you evolve this torus around the black hole, it starts accreting, and then at some point you develop this strong outflow around the polar region, essentially a jet. And and here as the red in the radial the z component of the VZ essentially means you have an outflowing matter, and this is driven by magnetic field, as you might see on the right. I've also been working on performing some simulations for magnetized binary neutron stars mergers, and using this Fuka importer provided by Sam Tootle. And here, for instance, you see a system where you have the merger, and soon after the merger, the remnant collapses promptly to a black hole. And instead, we have a different system where you have the merger, and then there is remnant neutron star produced, and this does not collapse at least up to 50 milliseconds after merger. At RIT, we're also interested to model the gas dynamics around the supermassive binary black holes. And there has been, as I mentioned earlier, there has been a recent work by Lorenzo Noci, a graduate student of Manuela, who actually recently graduated. And his work, he developed a lot of, in his work, he developed a lot of um, torrents or modules to support this kind of simulation. And our team at RIT ported some of these modules from Carpet to CarpetX to hand off what we call as a simulation from spherical NR. So what you do essentially is you have a circumbinary disk that you equilibrate with this code called spherical NR, and this is a simulation done by Lorenzo, or what you see on the left, and essentially, but then you have a cutout in the middle, and what we do then is you hand off to actually model the merger of the SMBBH, you hand off to a different Cartesian code. In this case, this is called, we hand it off to AsterX. And this is for a binary for plus spins plus zero point 0.9 plus zero point 0.9 at a 20 em separation. And we also evolve this with something called as a superimposed curl shield metric, and also include radiation cooling. So once we hand it off to AsterX, we are able to evolve and the system, at least for another 400M. We have also other simulations that go for much longer. This is they're done by Mikhail. And in this case, you see that the matter is starting to accrete, two black holes are starting to accrete matter from this circumbinary disk, and starting to form what we call as mini disk around these two black holes. Now, just to jump ship again and talk about a bit about performance, I think Leeway already gave a very nice introduction about how, sorry, um, the spacetime modules are performing with CarpetX. In this case, I talk about three different systems with AsterX. Essentially, these are a TOV and for setup A, which is evolved in Cowling spacetime. So you don't essentially evolve the spacetime. You keep it same as the initial data and using a uniform grid. And then there is a setup B where you actually evolve the spacetime using the Z4C thorn, again, still on a uniform grid. And there is a setup C that evolves the spacetime using 8 levels of AMR. For here on the right, I show strong scaling only for setup A and B. And as you might see that as you go from, say, 64 GPUs so to 8,000 GPUs, the scaling goes down by a factor of it, not a factor, but say up goes to about 20 to 20% or so. So it is quite bad, as Levi mentioned as well, because essentially what you do is as you move on to high number of GPUs, the workload per GPU, the compute load per GPU decreases by drastically from say 20 to 40 cubed to 48 cubed. So this is the reason of this decline. But for weak scaling, we do a bit better.
Jay,
Yes.
before you continue, can you go back one slide? Can you just maybe repeat what setup this is? So is this a binary, or is this a single black hole with matter on top? And are you comfortable telling us what happens in setup C when you have AMR?
Yes, a good question. So yeah, so this is essentially a TOV. And then there are three different setups. One is without evolving space-time, and this is only a uniform grid. So there is no AMR. Then there is a setup B where you have also evolved the space-time with the hydro evolution of the TOV. And this is again on the uniform grid. And then there is what we call a setup C, is where you evolve the spacetime and there is 8 levels of AMR involved. And yes, so as you see, maybe to go a bit more in detail, for example, in setup B, you increase the workload in terms of the number of equations you want to solve. So this is why the green curve is below the red one, because as the zone cycles per second decrease, um, but just to look at the scaling also, yes, it goes down to about 20% or so, if I remember correctly, compared to, I think, for 8-node performance. In the case of setup C, it is the zone cycles per second are at least a couple of factors lower. And I think in that case, you go to about 5 to 10% efficiency when you go to 8,000 GPUs. Now, again, these results this was done, I think, a year or two ago. There has been definitely been improvements, as what Liwei also mentioned in the code, where he removed these unnecessary prolongation sinks. And I think, for example, I think I recently did um, a strong scaling test for using, I think, 12 levels of mesh refinement for a binary black hole system. And for on one node, I think we are still able to maintain an efficiency of about 80% for strong scaling.
Okay, very good. Thank you. Are there any other questions? No? Anything online? No, then please continue. Thanks, Jay.
Thank you. Right, so for weak scaling, again, these results are old from the paper where for setup A, for example, when we have a workload of about 240 cube cells per GPU, we are able to maintain more or less 77% of efficiency, comparing, I think, to 8 nodes to 2048 nodes of performance, GPU nodes. And if you reduce your compute load per GPU, that is the lights red case. Again, this is all uniform grid. The efficiency goes to about 67%. And the scaling, in this case, when you have a setup which has 8 levels of AMR, which is in blue, it goes down to about 20 to 30% uh, when you go to 2048 frontier nodes. But now I think, again, like I mentioned recently, this update from Leeway has helped us get an efficiency of about 50% up to 2048 GPU nodes, compared to, I think, a 4-node performance. So also, as I mentioned, the subcycling in time has definitely helps quite a bit. In this case, you see that the blue curve gives you a zone cycle per second per GPU about, say, on the order of 10 to the power minus 2, like 10 to the power minus 6, or 10 to the power 6. And once you include subcycling in time, um, I think the absolute performance is increased by a factor, I think, 3 to 5. So that is a tremendous speed up when you include subcycling. Next, we tried to profile our code. So for instance, we use this NVIDIA Insight system to see if it's functioning as we expected. Uh, this is again it's an old profile, but just to see that here, what you see on the left, the black is where you have the CPU workload, on the blue is your GPU workload, and the red shows the memory transfer between GPU and CPU. So as you see that once you have your time steps, when your code is actually evolving, there is only blue, and that's what we want. That there is only the GPU functioning. There is no transfer between CPU and memory transfer between GPU and CPU when your evolution actually occurs. And there is also no CPU calls made or CPU work during this when your GPU kernels are evolved. This is good. Then we also looked at the trace to see which are the most expensive, what we call GPU kernels that are taking most of the computation and where we could actually optimize. So this is what we did using the software called HPC Toolkit. And we are able to recognize that the computation of fluxes is the most expensive and is the bottleneck of the code. And this is where we want to actually now optimize our code as well. That was all about GRMHD. I would quickly, in a couple of minutes, just talk a little bit about neutrino transport. I think there are already a couple of talks, maybe tomorrow, that are probably will go much more in detail. But again, why do we care about neutrinos? Is we want to, for example, understand our process nucleosynthesis in systems such as binary neutron star, black hole neutron star mergers, and see what these outflows come out as and how the YE distribution looks like, so that we can understand the composition in such events. Then you also have neutrino transport definitely plays a big role in the collapsar disk as well as core collapse supernovae. And some of these simulations, what I show here, which we find in literature. I'm not going to go through the background equations, but just say that generally, typically people consider evolving 3 neutrino species that contribute to your T mu nu as a T-rad, and these 3 neutrino species essentially are the electron, anti-electron, and the other combined effect from the other neutrino species. And here too, we care about solving the neutrino PC evolutions can be described as a function of can be evolved via the Boltzmann equation. That's what I show here, where this can become a very challenging problem. It's essentially evolving the three directions as well as the three momenta for each of the neutrino species. This can be a very expensive challenge. So there are people resort to either approximate methods such as Likert schemes or truncated moment schemes, or as well as exact methods as well, like Monte Carlo and the guided moments. I think Manuel will talk about it tomorrow. So our first approach, the main goal for us also is to move towards this guided moment scheme. So you would couple M1 plus, for example, MC. Here I just quickly, we started on our work in RIT on M1. So this essentially involves evolving conservation equations for the energy density, that's the M0, the first moment, and the the second moment for the fluxes, neutrino fluxes, or flux density. And these are these conservation equations. And there are also these interactive fluid and neutrino interaction terms that we need to consider, which include the opacities and as well as the scattering as for absorption and other such interactions. Um, and then you also need to close this equation, these two equations, moment equation, by providing the second moment, the pressure moment. And there are different analytical expressions to do that. Again, not going into detail, but yeah, so that's usually what you would comprise an M1 scheme. And then you also have, we would notice that this evolution equation also consists of some stiff terms, and then needs some special attention and special methods like implicit explicit solvers to compute those as we evolve such equations. This was all to come to this slide. This is what I wanted to talk about, is what we've started a pod of something called as a already existing code, which is called the THC-M1 by Radice et al. And this is, again, an open source development. You can find that on this link. And currently, we have ported our team, including Alan Wen, Mikhail, Liwei. We have ported the core algorithms of this code. And now we're currently working on porting some of these auxiliary dependencies from THC so that we can be independent from the THC code itself. And the next steps in the coming weeks and months would be to actually compile the code and reproduce some of the test problems that have been shown in this Radice et al. And then another thing is there are some root finders and other algorithms that are dependent on the GSL library within THCM1, and these are not GPU friendly. So we need to remove such dependencies and make sure that our new code is GPU, can be run on GPUs. And then finally, we want to couple this to matter evolution, to AsterX. And one of the other elements is to have a microphysical library that provides you these rates for different interactions for scattering, absorption, etc. And these libraries are typically publicly available, such as weak rates or BNS new rates. And we want to couple our new X to these libraries. And I think hopefully with that, we will be able to evolve BNS with tabular equation of state and also including neutrino transport and GRMHD. With that, I stop here. I would be happy to take any questions or comments or suggestions. Thank you very much.
Okay, thank you so much for your fantastic talk, Jay. Do we have any questions? Yes, Johnny.
Hi, Jay. Can you hear me?
Yes. Hey.
Thanks for the talk. I have a question actually way back in the photon leakage scheme. So I'm wondering, when you calculate the optical depth, like is this done with the AMR or dynamical AMR with AsterX?
I think the optical depth, as far as I know, is just analytical prescription. I'm not 100% sure how well it works with AMR, but from what I remember, I think Mishi was doing some tests to see how the implementation works. So I unfortunately don't have much on how well it does with AMR.
Thank you.
So first Roland, and I think then you, yeah?
Okay, thanks. Thanks for the talk. This was very interesting. I have a question about implementation. So you're using David's M1 code, and this is the second implementation that uses David's code. And I'm kind of asking, okay, was there a particular reason why that one was chosen? Were it just because it's open, it's already using the Einstein Toolkit, so it seems straightforward? Another one might have been to use the Tornado code by Vasilios Mevas et al. I think Vasilios is actually in the room right now. That might have also been an option. Can you elaborate?
Right. So I think this was just knowing that at this point, this THCM1 was publicly available, so it would have been easier to port. I think THCM1 is also carpet based, so I think the port would have been, at least in my, I haven't worked with the Tornado code, so I don't have much knowledge of that. Of course, Vasilius could correct me or inform me better. I'm also looking forward to his talk. But yeah, the main reason was that it is publicly available. It's very well tested, has a number of papers based on it. And also it was developed within the Einstein Toolkit infrastructure. And also David is also very approachable and friendly, and also are his graduate students. So in fact, Maitreya is also a friend. So this is also the reason why, it's easy to collaborate.
Okay, so we have another question. So by the way, Vasilis is in the room, and you probably didn't see him wave in response. So we have a common question here.
Yes, thank you again for your talk. I just had a bit of a curious question, and feel free to correct me if I'm wrong, of course. But from my understanding, when you look deep into the THC code, some of the rates calculations are actually, if you look at the lower level, those rates calculations are used not only in THCM1, but also in the leakage code, which is a nice addition to be able to reuse some code without having to get those rates calculations, redoing all those rates calculations. So I wanted to get your opinion on something. Say if you can reuse some of those rates from leakage to M1, which is seen in THC, do you think that if we move from photon leakage to M1, something similar could occur, that you'd make the rates calculations for a leakage code and then be able to use those same rates calculations in a photon M1 scheme?
Good question. And so just to understand better, do you mean that you evolve a leakage scheme and at the same you compute those rates and then you use that rates again in?
No, it's just that
the rate calculations themselves.
The rate calculations themselves, like the in THC, that the code it has that dual purpose. Like you can use you're not running the leakage code, but you can use the rates functions in the M1 scheme.
No, I definitely agree with you. That definitely can be done. That should be done also, because that will make our lives easier, as you mentioned. So yeah, that can definitely be used. Of course, as long as those rate calculations are physically sound, and I mean, of course, I assume they would be, so they can be done. And in fact, to point that out, I think at some point at RIT, there is also intention to use the M1 scheme for also photon radiation. So I think I assume some of these rate calculations would overlap.
Okay, thank you.
Thank you.
Okay, are there any other questions? Did you want to call? Okay, so Vasilis actually has a comment.
Thanks. Yeah, I wasn't going to talk about Tornado, but I wanted to shamelessly and selfishly pitch weaklib as yet another
Right.
microphysics library that does EOS and all the rates. And we're currently adding muons, so
Oh, cool.
if you want to have muons in the future, that could be interesting for you. As for Tornado versus THC, I guess I understand that if one is in the Einstein Toolkit world already, it might be a bit more of an effort to get a completely new code in. But I don't foresee huge issues because we've already coupled standalone Tornado with flux-conservative, which is another code that does hydrodynamics, and I'm going to talk about that on Thursday. So we can certainly talk about these things.
Oh, no, that's definitely useful to know, because I think for weak rates, I think that's one of the libraries that existing. It's, I think, completely written in Fortran, and we are thinking of actually porting it to, C++, and that would be an effort. So if weaklib is much more easier to integrate with, I think that would be very beneficial. And as you said, there are also now interactions for muons as well, so that could be interesting. So I definitely would like to talk to you about this in the future. Thank you.
Great, thank you. Are there any other questions or comments? Okay, I'm not seeing anything in the room. Just give me a second to go back to Zoom. Okay, I'm also not seeing anyone online. So I would say, Jay, I don't know if you want to stop sharing your slides so we can actually see you. So thanks a lot again, Jay, for your talk.
Thank you so much.
Okay, very good. So I think in terms of announcements, we have our lunch break now until 2 p.m., right? That's right. And